Rhombuses, rectangles, and squares. All of these are examples of quadrilaterals. They're all four-sided figures. But more importantly, they're all examples of parallelograms, which means that they carry any properties that we have proven for parallelograms thus far. That would be that opposite sides are congruent, opposite angles are congruent, and the diagonals will bisect each other. However, these are very particular types of parallelograms. They each have a certain aspect to them that makes them unique, which is really part of their definition here. And what we're going to do is just identify what those are at the beginning. A quadrilateral is a blank if and only if. So notice that biconditional statement here, using that as a definition. A quadrilateral is a blank if and only if it has four congruent sides. All right, so as you look at the different shapes and you imagine them, rectangle does not fit that definition. These do fit that definition. The better answer here is going to be a rhombus. That is its definition. All right, and that's going to make a little bit more sense when we get to the last one here. Okay, but by definition, a rhombus is a quadrilateral that has four congruent sides. It then becomes a parallelogram, and it carries all those properties that a parallelogram has. Next one, a quadrilateral is a blank if and only if it has four right angles. All right, between the other two, they both actually have four right angles. Okay, the one that's going to fit the definition, though, is going to be rectangle. A rectangle has four right angles. That's its definition. It then becomes a parallelogram and carries all those properties just like the rhombus did. And now, a square will be the last one because it fits both of those things. It's a unique quadrilateral that is a rhombus and a rectangle. A quadrilateral is a square if and only if it is a rhombus and a rectangle. Of course, that means you could also say a quadrilateral is a square if and only if it has four congruent sides and four right angles. All right, for this video, we're only going to be doing one proof today. You've already done a lot of proofs for the other videos, so we'll keep it real short and simple here. Just do one. So example one, prove if the diagonals of a parallelogram are perpendicular, then that parallelogram is a rhombus. All right, so let's go ahead and add in some diagonals. And by the way, as I add these in here, I want you to know that the picture that I chose to use here is a rhombus. Okay, I didn't want to draw a random parallelogram because in the end it will turn out to be a rhombus, and if I did a random parallelogram, the intersection that I would get here would not actually look like a right angle, which is part of the prompt, and that would end up being very misleading as we go through things. So I went ahead and started with what would be a rhombus for the shape. Okay, and we are told that we have a perpendicular here. That is our given. That is our setup to the problem. Okay, so step one, let's go ahead and write that down. Actually, let's label some stuff. Let's call that A, B, C, D. Okay, and we can begin with AC is perpendicular to BD. Segment. That is your given. That is your prompt right there, right? That you have a parallelogram and your diagonals are perpendicular to each other. Okay, now, because they're perpendicular here, all of the angles that are going to be in that spot are going to be 90 degrees. We only put a box in one of them, but they're all going to be 90 degrees. Okay, so what I'm going to do is label all of them. Let's go ahead and call them 1, 2, 3, and 4. Okay, and then for line 2, I'm going to write down that angle 1 is congruent to angle 2. They're both going to be 90 degrees. And I'm going to extend that out and say that it's also congruent to angle 3, because that's 90 degrees as well. And extend it out to say that angle 4 is also congruent to them, because they're all 90 degrees. Okay, and my reason for that is that these are perpendicular lines. Okay, let's just write it that way. These are perpendicular. Let's call it the definition, because that is the definition of perpendicular. All right, so definition of perpendicular lines. All right, the definition of perpendicular lines, they meet up at a right angle. We could actually extend out, like how we're writing all this part up here, really get into the fact that they're the measure of 90 degrees, that because they're all 90 degrees, they're congruent. But we're going to go ahead and just skip ahead and say, look, in the end, they're all going to be the same because this is perpendicular over in that area. All right, and then for line 3, what I'm going to do is refer to something that we've proven about parallelograms, which is that the diagonals will bisect each other, okay? So in the picture, I didn't label this as a point, but I've been using P in the other videos, so let's call that point P over there. Okay, I don't know how well that looks, but that's a little arrow pointing there and says that's point P. And we can write down, get it mixed up here. All right, we can write down that AP is congruent to CP. We can also write down that BP is congruent to DP. That's that bisecting there. So let's record that. AP is congruent to CP. BP is congruent to DP. And that is because the diagonals of a parallelogram bisect each other. Not really a short way to write that one, but we've proven it before and we know that that's true. And then, if you take a look here, every one of the triangles that we have has the identical markings in them. Each of these, so there's 4 of them, right? They each have a single mark side, they have a double mark side, and then the angle that sits between them is 90 degrees. You've got single, you've got double, 90 degrees, single, double, 90, single, double, 90 degrees, which means that all 4 of the triangles are going to be congruent. Okay, so we're going to write sort of like this, a really extended out congruent statement here. We're going to do ABP okay, ABP is going to be congruent, and if we follow this the right way, it's going to be CBP, which is going to be congruent. We'll go ahead and just write it in the next line here. CDP, and that'll also be congruent to ADP. Yeah, and that's it. So all 4 of them are congruent to each other. Reason, side, angle, side. Okay, for all of them, they're all congruent by the same shortcut here. The side, angle, side fits. All right, and then line 5, let's see. Sometimes we got to reset and remember, what is it that we're trying to prove here? In this case, we're trying to prove that the overall figure is a rhombus. And to prove that, you got to fit the definition. The definition is that all the sides are going to be congruent. That AB would be the same as BC, same as CD, same as DA. And look, if all the triangles that I have here are congruent to each other, then we can say that. We can say that AB is congruent to, well, in the order I'd write it would be CB, would be congruent to CD and AD, and all of that is because of corresponding parts of congruent triangles. And 6, we could go ahead and just make the statement that ABCD is a rhombus because of the definition. Not 2 ofs, of A. The definition is that all the sides are congruent. That's what we've proven here. We're good to go.
Later, blah.